In this video, we're talking about directional derivatives, and in this particular problem, we've been asked to find the derivative of the multivariable function in the direction of the vector v at the given point p, and we've been given the function f of xy is equal to x squared plus 2xy plus 3y squared. We've been asked to find the derivative of this function in the direction of the vector v equals 1, 1 at the particular point 2, 1. So you can think of a directional derivative in the same way that you would think of velocity. Remember that velocity indicates two things. It indicates speed, but speed in a particular direction. So there's sort of two components to a value for velocity. Well, in the same way, a directional derivative has two components. Not only does it tell you the derivative, but it tells you the direction in which it occurs. So that's why a directional derivative is so powerful, because you sort of get two pieces of information from finding the directional derivative. So this formula here for d sub u, this is going to be the directional derivative of the function f of xy. So as you can see, we're going to need to find values for a and b, and we're also going to need to find the partial derivatives of the function with respect to x and y. So the partial derivatives will be pretty simple, but what values are a and b? Well, a and b are going to come from the unit vector u, and we can find the unit vector using this formula here, where c and d come from the vector v. So sometimes in a problem like this one, you're going to already be given the unit vector u. In that case, for example, if we had u equals 1, 1, we would just be able to plug these values 1 and 1 directly into our directional derivative formula for a and b. But when you're given a vector v, you have to convert it into its unit vector form and then grab a and b from the unit vector to plug into your directional derivative formula. So let's start by finding our unit vector, and in order to find the unit vector, we're going to use this formula right here. Well, in our case, we have the vector v, 1 and 1. C and D come from that vector v. So these are the values of C and D. They're both 1. So if we plug those into these formulas here, we're going to say that the unit vector u is going to be equal to, here we have c, well we know c is 1, divided by the square root of c squared, well that's 1 squared, which is just 1, plus d squared, well d is 1, 1 squared is still 1, so 1 plus 1, like this. And then same thing here, we have d, which is 1, divided by the square root of c squared plus d squared. So we already know that that's the square root of 1 plus 1. So real simple, we just plug those values in, and now we're going to simplify. So we're going to say the unit vector is equal to 1 plus 1 is 2, the square root of 2, we'll just have square root of 2, so we're going to have 1 over root 2, comma, 1 over root 2 for the unit vector. Then we can say that these values we just found are the values a and b that are going to get plugged into our directional derivative formula for a and b here. So now we just need to find our partial derivatives, partial derivative of f with respect to x and of f with respect to y. So partial derivative of f with respect to x, coming back to our original multivariable function, if we take the derivative with respect to x, we get 2x plus 2y, and this derivative of 3y squared is 0 because there's no x variable involved. The partial derivative of f with respect to y is going to be 0 for the x squared, here plus 2x, and then plus 6y. So now what we could say, if we plugged everything into our directional derivative formula, we would get d sub u, in other words, in the direction of this unit vector u that we found, of f of xy, so of f of x y is going to be equal to a, which we know is 1 over root 2, multiplied by the partial derivative of f with respect to x, which we know is 2x plus 2y, plus b, which we know is 1 over root 2, so 1 over root 2, multiplied by the partial derivative of f with respect to y, which we found was 2x plus 6y. So this is the formula that models the directional derivative everywhere in the direction of the unit vector u, but remember we're interested in the specific point 2, 1. So what we want to find is d sub u of f of 2, 1, which is going to be equal to 1 over root 2, and here of course we're just going to plug 2 in for x and 1 in for y. So plugging 2 in for x, we're going to get 2 times 2, which is 4, plus 2 times 1, because we're plugging 1 in for y. So 4 plus 2 is going to give us 6, plus 1 over root 2 multiplied by 2 times 2 is 4, plus 6 times 1, we get 10. And now we're just going to have 6 over root 2 plus 10 over root 2 is going to give us 16 over root 2. And of course we want to rationalize our denominator, so we want to multiply this by root 2 over root 2. When we do that, we'll get 2 in our denominator here, and then we can cancel 2 from both the numerator and the denominator. So dividing 2 by 2, we get 1. Dividing 16 by 2, we get 8. So we end up with 8 root 2 all divided by 1. So we can say d sub u of f of 2, 1 is going to be equal to just 8 root 2, because of course the 1 in the denominator is redundant, so we can just call this 8 root 2. So 8 root 2, that value right there, is the derivative of the function f of xy in the direction of this unit vector u, or the vector v, at the particular point p, 2, 1.